Welcome to another lesson of sectoral structures theory. We're going to continue with the partial sums transformation. We will look at two problems today and try to solve them. The first one is a pretty straightforward concept. So we have a sectoral structure AN whose partial sum or whose sigma bar is isomorphic to 4,3 subscript 7. So not necessarily equal, but isomorphic. So it could be equal, but it could also just be isomorphic to it. The additional criteria is that the boundary of the conjugate of AN is less than 24. What does that mean? So the boundary, if you remember, the boundary of AN is the length of its structural curve plus the length of its walk. So if we have a sectoral structure, let's say something like this, then the boundary would be the curve, which is equal to 2 pi, and the walk, which is equal to 2 times lambda. Notice that all sectoral structures by definition have the same area. So they all have an area of pi. But the perimeter, not if we include both the walk and the curve, varies. So in this case, we're not concerned with the boundary of the sectoral structure itself, but the boundary of its conjugate. Why would we see criteria like this? Because we know that all isomorphic sectoral structures by definition have the same boundary. So it wouldn't make sense to put a boundary restriction on a set of isomorphic sectoral structures. However, even if two structures are isomorphic, their conjugates will not have equal boundaries. So let's define this part, the 4,3 subscript 7, as sigma bar of Bm. So we've introduced another sectoral structure. And now we can write the equation as sigma bar of AN is isomorphic to sigma bar of BM. And we saw earlier that if the two partial sums are isomorphic to one another, then the two structures are also isomorphic to each other. And you can go back to the prior lesson. So therefore, we know that AN must be isomorphic to Bm in this case. And what is Bm? Bm is simply the inverse partial sum of 4,3 subscript 7. Therefore, we can say that the order of Bm has to be 1 more than the order of this, which is 2 plus 1 equals to 3. So the order must be 3. So Bm must be made of 3 parts, and we can figure out what these 3 parts are. We know that the last parts, W2 and W3, must add up to 3. So we have two options, either 2 plus 1 or 1 plus 2. So here we have 2 and 1, and here we have 1 and 2. And we can easily figure out W1 because it must add up to 4 when we add it to W2. So therefore we get two sectoral structures for Bm, 221 subscript 5 and 312 subscript 6. So what can we say about AN? AN must be isomorphic to these two sectoral structures. So if you remember, we said that we introduced the concept of fitting earlier, which is similar to inclusion, but it means that AN fits into this set. So that means that it is isomorphic to these elements here. So we will say AN fits into the set 2 squared 1 subscript 5 and 312 subscript 6. Let's try to figure out a little bit more. We got pretty far. Now let's introduce the next condition. So we've seen earlier that the order of a sectoral structure plus the order of its conjugate is equal to n plus 1, which is the degree of the sectoral structure plus 1. We know that the degree of the sectoral structure AN is equal to 3. We established that already. So we will say 3 plus the order of the conjugate must equal to n plus 1. Therefore, the order of the conjugate must equal to n minus 2, simply by moving the 3 to the other side. So this is a criteria that we established. Now let's go back to the boundary. The boundary of the conjugate of AN will be equal to the walk of the conjugate plus its curve. The curve is 2 pi, and the walk is 2 times lambda of the conjugate. We're going to substitute lambda of the conjugate. We're going to substitute this, n minus 2. So this gives us 2n plus 2 pi minus 4. So this gives us the boundary of the conjugate, this right here. Now, we also know that the boundary should be less than 24. That's the condition we established. So the boundary of AN conjugate should be less than 24. So 2n plus 2 pi minus 4 should be less than 24. This simplifies to n is less than 14 minus pi. Now 14 minus pi, let's say pi is 3.14 approximately. 14 minus 3 is 11, and it's going to be a little bit less than 11. However, since n must be a natural number, then n must be less than or equal to 10. So let's go back now to Bm. 2 squared 1 subscript 5 has a degree less than 10, so this one works. 312 subscript 6 has a degree less than 10, so this one works. But we're also going to look at their isomorphic structures. So we multiply this by 2, we get 4 squared 2 subscript 10, it works. Multiply this by 2 and we hit a degree of 12. So that's where we stop. So therefore, now we've solved for AN is one of these 3 sectoral structures. So let's look at this interesting problem here. The partial sum of the involute of a sectoral structure is equal to the conjugate of that sectoral structure. Let's see what structures meet this criteria. So we're going to begin by looking at the order of the structure that we're working with. We know that the order of the involute is equal to the order of the sectoral structure because we're just rearranging. We also know that the order of the partial sum of the involute will be, or of any sectoral structure, will be 1 less than that structure. So we can substitute lambda of AN minus 1 on the left here. So we can see it here. And then we also know that the order of the conjugate plus the order of the sectoral structure should equal to n plus 1. So we're going to solve for the order of the conjugate, which will be n plus 1 minus the order of AN. So we have this equation here with only one variable, which is lambda of an. We will say that 2 lambda an is equal to n plus 2. Therefore, lambda is equal to n over 2 plus 1. So we already have a hint here that n must be an even number for this to work. Because if n is odd, then you'll end up with fractions. You can't have a fraction for the order. Or we can express this as n equals to 2 lambda minus 2. We also know that the degree of the involute is equal to the degree of the sectoral structure. Again, because it's just a rearrangement. And the degree of the conjugate of a sectoral structure is equal to the degree of that same sectoral structure. Because when we're doing the conjugate, we're only changing the joints. We're not changing the number of sectors. So we can say that the degree of the partial sum, or this is what we're trying to solve for, the degree of the partial sum of the involute of a sectoral structure should equal to the degree of the conjugate. So this is what we want. Since the degree of the conjugate and the sectoral structure itself are the same, we will say that the degree of the partial sum of the involute is equal to the degree of that sectoral structure that we're looking for. So when is that the case? Because we know when we take the partial sum, most of the time the degree will increase because we're going to be adding more sectors. However, we know that for theta structures, so order 1 structures, the partial sum gives us the same structure, so the degree stays the same. And there's another case when we have order 2 structures, such as 3, 2, subscript 5, the partial sum will give us 5 subscript 5, so the degree stays the same as well. So really, what we know is that for the degree to stay the same, the order of the sectoral structure must be either 1 or 2. And we've already said that based on this, we know that the order cannot be an odd number, or the degree cannot be an odd number, so it must be an even number. Let's use this as our guide. So the order must be either 1 or 2. Let's look at order 1. So if the order is 1, then the degree will be 2 times 1 minus 2 is 0. We can't have a degree 0, so that's not possible. Let's look at order 2. 2 times 2 is 4 minus 2 is 2. So in this case, n will be equal to 2, and the order, and lambda will be equal to 2. So there's really only one sectoral structure that meets the criteria of degree 2 order 2, and that is 1 squared subscript 2, also known as xi 2. And we can double check, and this is the 1 squared subscript 2 structure. So let's take the involute of 1 squared subscript 2 is the same structure itself, as we can see here. It's just reversing places. The partial sum of this will give us the theta structure 2 subscript 2. Let's look at the conjugate. So the conjugate, we have to change this beta joint into an alpha joint. So this becomes 2 subscript 2. Or theta 2, so that is correct. So really we started with a very generic equation, but it ended up to have only one solution.